Here's the thing that pulled me into this one. We know the date. January the 26th, 1700. We know it was evening, somewhere around 9 o'clock, and nobody on that coast wrote a single word of it down. That's the bit I love. An earthquake that happened 100 years before anyone in the Pacific Northwest was keeping written records, and we've got it pinned to a specific evening in January. So tonight we're going through how on earth that happened. The fault itself, the dead trees, the paperwork in Japan, the stories that were already there, the mud on the sea floor, and yes, eventually the odds on the next one. I'll give you the answer to the title now, because I'm not going to make you stay awake for it. No, the West Coast is almost certainly not about to relive 1700. The honest figure is roughly a 15% chance in the next 50 years, which is not nothing, and is also not a countdown. We'll get to why later. If you like this sort of thing, subscribing helps. Right. Let's start with the fault. If you pull up a map of the west coast of North America and ask the average person to name a fault, you get one answer: the San Andreas. Every time. It's been in films, it's had its own disaster movie with The Rock in it. It's basically a celebrity. Ask that same person to name the other one, the bigger one, the one that runs offshore. From the middle of Vancouver Island all the way down past the Oregon border into Northern California, and you'll mostly get a blank look, which is fair enough. It doesn't have a film. It barely has a reputation outside the region it sits under. And for most of the 20th century, it didn't even have a threat assessment, because the general professional opinion was that it wasn't really doing anything. It's called the Cascadia Subduction Zone, and I want to spend a bit of time on what it actually is before we get anywhere near what it did, because the mechanics are genuinely satisfying once they click. So, a subduction zone. The outer shell of the planet is broken into plates, and those plates are all shuffling around at roughly the speed your fingernails grow. When two of them run into each other, one of two things happens. Either they grind past each other sideways, which is what the San Andreas does, or one of them loses and goes underneath. That second one is subduction. The loser goes down into the hot part and gets slowly recycled. Off the coast of Washington and Oregon, the loser is a plate called Juan de Fuca. It's small, it's oceanic, and it's heading east-northeast at about 1.6 inches a year. The North American plate is coming the other way, west-southwest, at about an inch a year. Nobody involved is in a hurry, but they are absolutely unambiguously going to meet, and the thing about oceanic crust is that it's dense and heavy, so when it meets a continent it does the geological equivalent of ducking. Down it goes, at a shallow angle, underneath everything from Vancouver Island to Cape Mendocino. And as it descends it heats up, and it starts sweating out water, and that water rises into the rock above it, and lowers the melting point, and you get magma, and the magma comes up. That's the Cascades. Rainier, St. Helens, Hood, Baker, Shasta, the whole postcard. Those mountains are the exhaust system of the fault. They're what a subduction zone looks like from 100 miles inland. I think that's a lovely bit of joined-up thinking, personally. You look at Mount Hood on a clear morning, and you're looking at the direct consequence of a plate going under your feet at fingernail speed for millions of years. The fault itself is the surface where the two plates are actually touching. Geologists call it the megathrust, which is an unusually blunt name for something that spent decades being ignored. A small tangent, while we're here, because people ask this and I think the answer is more interesting than it gets credit for. Why do the plates move at all? What's pushing? Two things, mostly. One is that out in the middle of the ocean there's a ridge where new sea floor is being made. Magma coming up and cooling and adding itself to the edges of the plates either side. Fresh crust is hot and it sits high, and as it cools it gets denser and slumps downhill, and the whole plate slides off the ridge under its own weight. That's called ridge push, which is a slight misnomer because nothing's really pushing, it's more of a very slow, very large landslide. The other thing, and this is the one that does most of the work, is that the leading edge of the plate, the bit that's already gone down into the mantle, is cold and heavy and it's sinking. And it's still attached to the rest of the plate, so it drags. The plate is essentially being pulled off the table by a bit of itself that's already fallen off the edge. That's slab pull, and it's the dominant force in the whole system, which means Juan de Fuca isn't being shoved under North America. It's being pulled under by its own dead weight, and North America is just in the way. There's a ridge doing the pushing end of that job, incidentally, and it's not far offshore. The Juan de Fuca Ridge runs up the seafloor a few hundred kilometers out, quietly manufacturing new plate, which is why Juan de Fuca is such a small plate. It's being made at one end and eaten at the other, and it's losing. Badly, in fact. It used to be enormous. Juan de Fuca is what's left of a plate called the Farallon, which was once one of the great slabs of the Pacific and is now essentially gone, subducted under North America over tens of millions of years. What's off the coast of Washington today is a scrap. There's another scrap called the Explorer up by northern Vancouver Island, and another called the Gorda down by California, and that's it. 3 fragments of a dead giant still going under, still making mountains, still stuck. I find that quietly melancholy, and also completely irrelevant to the earthquake, so let's move on. One more thing before the argument, because it explains the timing of the argument. In May 1980, Mount St. Helens took the top off itself in front of a national television audience. Everybody knows the footage. And the thing that eruption did, apart from the obvious, was remind an entire country that the Pacific Northwest is a place where a tectonic plate is going underneath another tectonic plate right now, currently, as an ongoing concern. You cannot get a Mount St. Helens without subduction. The volcano is only there because of the fault. So the eruption was, in a very direct sense, the fault announcing itself, and a lot of people who had never given the geology of that region a second thought suddenly had reason to. That's the atmosphere the argument happened in. Ash on the cars in Yakima, and a licensing question about reactors, and a decade-old suspicion that the quiet fault under everything might not be as quiet as advertised. And here's the part that explains the ignoring, because it's the whole reason this story exists. Cascadia is quiet. Not quiet in the sense of not much going on. Quiet in the sense of almost nothing at all. Most subduction zones in the world are noisy. They grumble. Japan gets small and medium quakes on its megathrust constantly, as background hum. Chile the same. Alaska the same. It's the normal behaviour of 2 enormous slabs of rock scraping past each other under pressure. Bits of them slip a little, catch, slip again, and every slip is an earthquake, and most of them are too small to notice, but the instruments see them and you build a picture. Cascadia does hardly any of that. Very few small to moderate earthquakes have ever been observed on the megathrust itself. It just sits there. 2 ways to read that. Reading 1, nothing is happening here. The plates are sliding past each other smoothly. No friction, no stress, nothing building up. Move along. Reading 2, nothing is happening here because the 2 plates are welded together by friction, and the strain is going somewhere else, which is into the rock itself, and it is not going to stay there forever. For a long time, the field went with reading 1. And I want to be fair about that because it's easy to look back and be smug. There genuinely was no positive evidence for the other reading, no local written records of a great earthquake, because Europeans didn't chart this coastline until the 1770s and didn't settle it in numbers until the mid-1800s. No instrumental record, because seismometers hadn't been invented yet. So you had a fault with no history of doing anything, in a region with no history of anything happening, and everyone drew the obvious conclusion. The argument that eventually flipped it ran for about a decade, roughly from the late 1970s into the late 1980s, and it had a wonderfully unromantic trigger. It wasn't curiosity, it was nuclear power. People wanted to build reactors in western Washington and Oregon, and northern California, and when you want to build a reactor, somebody has to sign a piece of paper saying how hard the ground can shake at that spot. That question suddenly had money and politics attached to it, and a decade-long professional row broke out over whether Cascadia posed an earthquake threat at all. I find that detail quietly hilarious. One of the most significant hazard discoveries in North American geology got started because a licensing form needed a number in a box. The first proper crack in the silence equals safety idea came from surveying, not seismology, surveying. John Adams, then at Cornell, went and looked at old resurveys of highway benchmarks. These are the little brass discs bolted into bridges and rock faces that road engineers use as reference points, and every so often somebody goes round and remeasures them all to make sure nothing's moved. It's about as glamorous as it sounds. And when Adams stacked the resurveys up across decades, he found that the coastal regions of Oregon and Washington were being slowly tilted eastward. Tilted. The whole coast. Bending inland, very slightly over years. That's not nothing happening. That's rock being squeezed. If the plates were sliding past each other smoothly, the coast would sit still. A coast that's bending is a coast attached to something that's stuck. Around the same time, Tom Heaton and Hiru Kanamori did the comparison exercise. They looked at Cascadia's basic geophysical setup, the age of the plate going down, the angle, the convergence rate, the geometry, and asked which other subduction zones on Earth look like this. And the answer came back: southern Chile. Southern Chile, where in 1960 the planet produced the largest earthquake ever recorded by instruments. Also Alaska. Also the Nankai Trough off Japan. All places famous for exactly the sort of event that Cascadia was supposedly incapable of. That paper landed in 1984 and from what I can gather was met with a fairly cool reception, which again, fair, it's an argument by resemblance. It says this thing looks like those things and those things do something terrible, so maybe. It doesn't say it happened. Nobody had a single scrap of physical evidence that Cascadia had ever actually ruptured. That came later, and it came from a marsh, and we'll get there. What I want to leave you with from this section is the shape of the thing, because the shape matters for everything that follows. You've got a fault around 600 miles long, running offshore, mostly underwater, mostly out of reach. Part of the interface between the two plates is locked, genuinely stuck, welded by friction, not moving. Meanwhile, the plates themselves keep converging, because they don't care that the fault is stuck. They're driven by the whole engine of the planet's interior, so the rock in between deforms. It compresses and bends, and it stores that deformation like a spring, and it will keep storing it until the friction gives out. And because the locked zone is both long and wide, when it does give out, it can give out over an enormous area at once, which is what makes the biggest earthquakes on Earth. Magnitude is basically a function of how much rock moved and how far it moved. A short fault can only ever make a medium earthquake, no matter how angry it is. A fault the size of Cascadia has room to make something very large indeed. That's the setup. Two plates, one stuck, strain going in and not coming out. Now, one thing before we move on, because it's my favourite fact in this whole section, and I've been sitting on it. The fault does move, regularly. It's just that nobody has ever felt it. Underneath the locked bit, deeper down the slope where the rock is hotter and softer, the two plates slide against each other in slow motion. Not in seconds, over days and weeks. The fault creeps along, releasing energy so gradually that it produces no jolt whatsoever, just a faint seismic hum that only shows up on sensitive instruments. It's called episodic tremor and slip, and it happens in Cascadia roughly every 8 to 22 months, like clockwork, if clockwork were a bit vague about it. So while everyone's arguing about whether the fault is active, the fault is in fact quietly moving under the whole of Washington and southern British Columbia on a cycle of about a year and a bit, and every single person walking around on top of it is completely oblivious. Has been the entire time. Still is. I think about that more than is probably healthy. There's a slow-motion earthquake happening under Seattle every year or so, and the only reason anyone knows is that somebody left a very good instrument switched on. There's a whole video in slow slip on its own, and I might make it because the physics of a fault that slides without shaking is properly strange, and I've barely scratched it here. But that's for another night. Anyway, that's the fault. Two plates, one stuck, the strain going in and not coming out, and a decade of people arguing about it with nothing solid to point at. What finally settled it came out of a marsh, and the man who found it was using a garden tool, which I'll get to in a minute. A nejirigama is a Japanese weeding tool. It's a short wooden handle with a flat blade set at a right angle, sharpened along one edge, and it's designed for kneeling in a flower bed and scraping the roots out from under things. You can buy one for about a tenner. Gardeners swear by them. It is by any measure an extremely unserious object. In March of 1986, at low tide, a geologist called Brian Atwater took one down to the beach at Near Bay, right up at the northwest tip of Washington, where the coast turns the corner, and started digging with it. That's the whole origin story. That's it. The thing that eventually rewrote the seismic hazard maps for 3 states, and a Canadian province started with a bloke and a weeding tool and a low tide. What he was doing there wasn't random, mind. The argument we talked about had been rattling on for years, all of it theoretical, all of it about resemblance and tilt and probability, and Atwater had gone off in a slightly different direction. He'd had a thought that I think is the single cleverest move in this entire story, and it's this. If the fault had ever ruptured, the land would have dropped, suddenly. And if the land dropped suddenly, then whatever was growing on it at the time went under salt water in an afternoon. And plants that go under salt water in an afternoon don't get the chance to rot properly or wash away, they get buried, which means the coast isn't just a coast, It's a filing cabinet. So he dug, and under a layer of sand he found arrowgrass. Arrowgrass is a salt marsh plant. Unremarkable, low, a bit rushy. The point isn't the species, the point is where it was. It was sitting in a layer of old marsh soil several inches down with clean sand on top of it, and it had been there for centuries. Now think about what that means. That marsh was, at some point, the surface. Sunlight, air, birds, the lot. It was the top of the world, and then it wasn't, and something dumped sand over it, and it stayed under for 300 years in good enough condition that a man with a garden tool could scrape it out and identify the species. Here's the logic that makes it evidence rather than a curiosity, and it's worth being precise about because everything downstream leans on it. Land goes up and down all the time. Sea levels rise, coastlines shift, marshes drown. That's normal. But normal is slow. When a marsh drowns gradually, over decades or centuries, you don't get a clean line. You get a smear. The salt-tolerant plants slowly outcompete the freshwater ones. The soil chemistry drifts. The boundary between one layer and the next is blurry and gradual, and takes a handspan of sediment to complete. Because that's what gradual looks like in mud. It looks gradual. What Atwater was looking at was not a smear, it was an edge. Marsh, then sand, and no transition worth mentioning. The plants at the top of that soil had been alive and getting on with it, and then they'd been under salt water, and there was nothing in between. That's not sea level rise. Sea level rise doesn't have edges. That's the ground dropping out from underneath a living surface in one go. Whether that's an earthquake is a separate question, and he couldn't answer it from one hole in one beach. So he went and found more holes. The next bit is the part I'd genuinely like to have seen. Atwater got a kayak and started going up the estuaries. Willapa Bay is down the Washington coast, a big shallow drowned river system full of tidal channels and mudflats and oyster beds, and it's the sort of place where the only sensible way to move around is by water. He paddled up the Neaweacum River, which is barely a river, more of a winding creek through the marsh grass, and he started reading the banks. And there they were, buried marshes, buried forests, the same sharp edge, over and over, at multiple sites, kilometres apart. I want to be clear about how unglamorous this is because I think it's the best thing about it. This is not a laboratory, there's no supercomputer. This is a man in a small boat in a cold estuary in the Pacific Northwest. In the rain, presumably, because it's always raining, poking at a mud bank and going, hang on. And then, because one buried surface is an anecdote and a stack of them is a record, he and a colleague called Eileen Hemphill Haley went at Willapa Bay properly and dug out the whole sequence. Not one drowning, several. Layered up like pages, each one a marsh that had been the surface and then abruptly wasn't, each one buried under the next. They got a record going back about 3,500 years, and in it they counted 7 earthquakes. 7. Including the most recent one, the one we're here for. And this is where I want to plant something, because it becomes important later, and I'm not going to belabor it when we get there. Those 7 were not on a schedule. At one of their sites, 3 of the events came inside a 500-year window. Bang, bang, bang in geological terms. And then in another part of the same sequence, roughly 900 years went by between one event and the one before it. 900 years of nothing at the same spot, on the same fault from the same process. So the fault does not tick. It's not a metronome. It's not a bus timetable. It is something considerably more annoying than that, and we'll come back to what that does to the maths at the end of the night. There's a second thing in those cores that I skipped past and shouldn't have, because it's half the argument. The sand. Remember the sand on top of the arrowgrass at Near Bay? Where does sand come from? In a marsh, in a sheet, laid flat over the top of a drowned lawn. Not from the river. Rivers deliver sediment in channels and lobes, and they do it constantly and messily. This is a sheet. It's thin, it's continuous, it drapes over the old surface following its contours, it's got beach material in it, and it thins out as you go inland until it disappears. That's water coming from the sea, fast, carrying beach with it and dropping it as it slows down. That's a tsunami deposit. And it's sitting directly on top of the drowned surface, with nothing in between, which tells you the order of events and how much time was between them, which is none. So each of those buried layers isn't just a subsidence event. It's a subsidence event with a wave on top of it, in the same layer, at the same moment. The marsh went down and the sea came in over it within, at most, the same hour. You can read that off a mud bank with your eyes, and that pairing is what turns it from an interesting drop in ground level into an earthquake, because there is nothing else in nature that lowers a coastline by a metre and throws the ocean over it in the same afternoon. Dating though, That's where the frustration comes in. The tool available at the time was radiocarbon. Everything living takes up carbon while it's alive and stops when it dies, and one flavour of carbon decays at a known rate, so measure what's left and you know how long it's been dead. Brilliant technique. Nobel Prize. Rebuilt archaeology from the ground up. And for something 300 years old it is, I'm afraid, nearly useless. The error bars are the problem. Radiocarbon on a sample that Young gives you a range of several decades if you're lucky and careful. And worse than that, the amount of carbon in the atmosphere hasn't been constant through history, so there are stretches where the calibration curve goes wobbly, and a single measurement can map onto 2 or 3 separate possible date ranges. The late 1600s and early 1700s are, of course, one of those stretches. Naturally. So Atwater, Minzy Stuver and David Yamaguchi ran a radiocarbon test in the early 1990s, specifically aimed at this problem, and it did what it could, which was narrow things and confirm the general picture. What it could not do was hand anyone a year, which is the state of play going into the trees. You've got a fault with a proven history of great earthquakes, a stack of them, irregular, at least 7 in 3,500 years at one bay alone, and the most recent one is somewhere in a window several decades wide. That's enough to redraw a hazard map. It's nowhere near enough to satisfy anybody. In 1987, Atwater published it in the journal Science. The paper was called More or Less Evidence for Great Earthquakes Along the Outer Coast of Washington State, which is about as understated a title as you can put on a document that tells several million people the ground they live on is not what they thought it was. And it worked. Not instantly, science doesn't do instantly, but it worked. Because the previous decade of argument had all been inference. Cascadia looks like Chile. The benchmarks are tilting. The plate is converging. All true, all suggestive, all deniable. Atwater turned up with mud. Mud that had been a lawn. Mud that had gone under in an afternoon, repeatedly for thousands of years, on a coast that was officially not doing anything. You can argue with a model. It is very hard to argue with a buried marsh. It didn't land as a thunderclap, mind you. Nothing in science does. The reaction was a long, slow, professional shuffle over years, as more people went out and looked in more estuaries and kept finding the same thing. That's how the field actually turns. Not one paper plus everybody else failing to prove it wrong for a decade. And the failing to prove it wrong is the important half. That's what most people miss about how this works. The paper isn't the evidence. The paper is a challenge. The evidence is what's left standing after everyone who'd quite like you to be wrong has had a proper go at you and come away empty-handed. Nobody came away with anything. The marshes were there. They're still there. You can go and look, which is more than can be said for most scientific results. One more thing about the method before we leave it, because it went a lot further than one coastline. What Atwater was doing has a name now, paleoseismology, reading earthquakes out of the ground rather than off an instrument, and the reason it matters so much is arithmetic. Seismometers have existed for about a century and a bit. That's the entire instrumental record of earthquakes on this planet, 100 and something years, and the events we're worried about happen every few hundred to 1,000 years. So the instrumental record for the biggest earthquakes is essentially a snapshot. It's like trying to work out how often a comet comes back by staring at the sky for an afternoon. You might get lucky. You'll mostly conclude wrongly that there aren't any comets, which is exactly the trap Cascadia fell into. 100 years of quiet is not evidence of a quiet fault. It's evidence of 100 years, which on the timescales that matter is nothing at all. It's a rounding error. Paleoseismology breaks that ceiling. It doesn't care about instruments. It reads mud, and mud has been keeping notes since long before anybody turned up. Suddenly, your record isn't a century, it's 10,000 years, and 10,000 years contains enough events to actually say something about the rate. That approach is now used everywhere. It got exported. People go and dig trenches across faults in California and Turkey and New Zealand and Japan, looking for exactly this sort of thing, and a good chunk of what the world thinks it knows about how often the big ones happen comes from that habit of reading dirt, which started more or less in a wet estuary in Washington with a kayak. What he had at that point was a sequence of events with no dates on them. He knew there had been great earthquakes, he knew roughly how many, and he knew the intervals were all over the place. What he did not know, and what nobody knew, was when. Radiocarbon can get you to within a few decades on something this old if you're lucky and careful, and a few decades is a fantastic result in geology, and completely useless if what you want is a date. So the fault had a history and no calendar. Getting the calendar took 2 more things. It took a stand of dead trees, and it took a filing system on the other side of the Pacific Ocean, which had been sitting there quietly holding the answer for 290-odd years without anyone thinking to ask. The trees are next. But before we leave the marsh, one more thought, because it's stuck with me since I started reading about this. Every single one of those buried layers is a moment, not a period, not an era, a moment. Each one is an afternoon when a place that had grass on it stopped having grass on it, and the whole record only exists because the drop was fast enough to bury the evidence before it could decay. The very thing that made the event catastrophic is the thing that preserved it. If the coast had gone down slowly, there'd be no record at all, and we'd still be arguing about whether the fault does anything. It's only because it happens all at once that we know it happens, which strikes me as a fairly generous arrangement. All things considered, the fault kept its own receipts. Picture a tidal marsh on the Washington coast. Flat, wide, grey-green, the kind of place where the horizon is mostly sky and the ground squelches. There's a river winding through it in slow, lazy meanders. Salt in the air, herons. And standing up out of the grass, scattered across it, are the stumps of enormous dead cedars, not lying down, standing. Silver grey, worn smooth by 300 years of weather. No bark left on most of them, no branches, just trunks going straight up out of a salt marsh, where no cedar would ever grow. Some of them are a good few feet across. They look like they've been put there. They're called ghost forests, and there are dozens of them up and down that coastline. The one on the Copalis River, a few miles northwest of Aberdeen, is the famous one. There's another at Nesquin down in Oregon that you can wander out to at low tide, and the first time I saw a photograph of the Copalis site, I genuinely assumed it was some sort of installation. Dead trees standing in a field of grass with no forest anywhere near them makes no sense as a natural object. It looks curated. It isn't, obviously. It's just what's left when a forest gets killed standing up. Here's what happened to them, and it's the same mechanism from the last section, seen from above the mud instead of inside it. The coastline dropped, between 1 and 2 meters straight down, and it did not come back. That's the crucial bit. This wasn't a flood. Floods leave. This was the land itself being demoted permanently, so that ground which had been comfortably above the tide line was now comfortably below it. And a western red cedar cannot cope with salt water. At all. It's a freshwater species. It wants a damp forest floor and rain, and if you put its roots in brine it dies, and it dies quickly. So an entire coastal forest, healthy, mature, hundreds of years old in places, was standing in the wrong place one evening, and was dead not long after. And you can go and stand in one, which I think is the strangest part of the whole business. The Nesquin one in Oregon shows itself at low tide, right off a perfectly ordinary beach with perfectly ordinary holiday homes behind it. People walk dogs past it. Kids climb on the stumps. It is a completely casual, unremarkable, slightly muddy feature of a nice beach, and it is also the visible wreckage of the largest earthquake in the recorded history of the continent, sitting there in public, free, no ticket required. I don't think there's another disaster on Earth you can do that with. You can't go and stand in Pompeii's afternoon. You can go and stand in Cascadia's evening, in Wellies, on a Tuesday, and buy a coffee afterwards. The trunk stayed up because cedar is absurdly rot-resistant. That's why people build things out of it. So instead of falling over and disappearing into the mud, they just stood there and weathered, and they're still standing there now, 3 centuries on, in a marsh, being photographed by geologists. This is the part where the whole thing turns from a nice bit of scenery into an actual clock, and I want to take it slowly because it's the neatest piece of reasoning in the entire story. Trees grow a ring a year. Everyone knows that bit. A good year gives you a fat ring, a bad year gives you a thin one, and you can count them and get an age. But there's a second thing rings do that's less well known and considerably more useful. Because the width depends on the weather, and the weather is regional, every tree in the same area gets the same pattern of fat and thin. A drought in a particular decade shows up as a run of narrow rings in every tree for miles around. A run of wet summers shows up as fat ones. So the sequence of ring widths isn't just a count, it's a barcode. And it's the same barcode across the whole neighbourhood, which means if you've got a living tree and you know what year each of its rings is because you can count backwards from the year you cut it, you've got a dated barcode. And if you've got a dead tree with no dates on it at all, You can slide its barcode along the living one until the pattern matches, and now the dead tree has dates too. That's dendrochronology, and it is not an estimate. It's not radiocarbon giving you a range and a confidence interval. If the barcode matches, you have the actual year. It's exact. So the question becomes, can you do that with the ghost forest? David Yamaguchi did. He went and cored the dead snags at Copalis, and cored living cedars on higher ground nearby that had never been touched by the salt water, and slid the patterns against each other until they locked. And the answer that came out was, the dead trees stopped growing between the summer of 1699 and the spring of 1700. There's a lovely wrinkle in how he got that precise, actually, and it's a properly good bit of fieldwork. The final rings, the ones that tell you the exact year of death, are the outermost ones, and on a trunk that's been sitting in a marsh being sandblasted by 300 years of Pacific weather, the outermost rings are the first thing to go. They're gone. Weathered clean off, so the trunks themselves can't give you the last few years, but the roots can. Down under the mud, buried the whole time, protected from the weather, the bark is still on. And under the bark, the last rings the tree ever grew are sitting there intact. So the answer was under the ground, in the roots, the whole time. You just had to be willing to dig. And that phrasing, summer of 1699 to spring of 1700, is doing something specific, so let me unpack it rather than leave it sitting there looking vague. A tree in that climate doesn't grow all year. It grows in the warm half and then it shuts down for winter. Nothing happens. No new wood. It's dormant. So the last ring on those trees is a complete ring. A whole year's growth, finished, done, with nothing started on top of it. That tells you the tree was alive through the entire 1699 growing season and got all the way to the end of it, and then it never started a 1700 ring. Which brackets the death. It's after the 1699 growing season finished, and it's before the 1700 one would have begun. That's the dormant window. Autumn, winter, early spring. The tree can't tell you which month, because it wasn't paying attention, it was asleep. But it can absolutely tell you it wasn't summer. It can tell you it wasn't a year earlier or a year later. The wood is that specific, and it's specific because of what the tree didn't do rather than what it did. January is in that window, comfortably. It wasn't just Copalis either, which matters more than it might sound. Gordon Jacoby and colleagues went after the same problem at other sites in Washington and northern Oregon in the mid-1990s, and got the same answer out of different trees in different places. That's the bit that makes it a rupture rather than a local event. If one stand of trees dies in one winter, that's a landslide, or a storm surge, or a river doing something odd. When trees die in the same dormant season across a long stretch of coastline in separate estuaries tens of kilometres apart, you're no longer looking at a local accident. You're looking at something that happened to the whole coast on the same night, and the fact it's western red cedar is a piece of luck we should probably acknowledge. Cedar is loaded with natural preservatives. That's the whole reason people have always used it for anything that has to sit outside and be rained on. It resists fungus, it resists insects, it resists rot in a way that is genuinely exceptional among trees. It's why the plank houses were cedar. It's why fence posts are cedar. It is nature's most stubborn timber, which means when a cedar forest gets killed and left standing in a salt marsh, it doesn't do what almost any other species would do, which is fall over within a few decades and vanish into the mud without trace. It stands there for 300 years, getting slowly sanded down by weather but fundamentally refusing to go away, until somebody turns up with a coring tool and asks it a question. If that coastline had been oak or hemlock or pine, we'd have nothing. The evidence would have rotted out from under us before anyone thought to look for it. The single most precise dating constraint on the largest earthquake in North American history exists because of the chemistry of one tree species that happens to be very hard to destroy. Now here's the bit that makes it an earthquake rather than a mystery. If those trees had drowned gradually, if the coast had subsided slowly over decades or a century, the trees would have got sick first. Salt creeping into the root zone, a bit more every year, is a slow poisoning, and a slowly poisoned tree announces it in the rings. You get narrowing. Year on year, thinner and thinner, the tree fighting and losing, and the rings get tighter until they stop. There is none of that. The rings are wide right up to the last one. Those trees were fine, 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 dead. No decline, no struggle, no warning. Whatever happened to them happened faster than a tree can react to, which, given that a tree reacts on a timescale of years, is not a high bar, but the point stands. There is no gradual signal in the wood because there was nothing gradual about it. That's what rules out sea level rise, subsidence from sediment compaction, a shifting river mouth, all the boring explanations. Boring explanations are slow, and slow leaves a trace, and there's no trace. The coast went down in one movement, and a forest went from healthy to dead with nothing in between. It's a bit like reading a receipt to find out when somebody died. There's something faintly absurd about the fact that the most precise dating evidence for a magnitude 9 earthquake is the growth habits of trees. But I've come round to thinking it's the most reliable witness in the whole affair. The wood doesn't have an opinion, it doesn't misremember, it just wrote down the weather every year until it couldn't. And what it wrote down was winter of 1699 into 1700, which is, and I want to be honest about this, an incredible result and also not quite enough. A season is not a date. Winter of 1699 to 1700 is a window several months wide. It rules out an enormous amount. It tells you it wasn't the 1600s generally, it wasn't a slow process, it was one event in one cold stretch at the turn of a century. That is an extraordinary thing to be able to say about an event nobody recorded. But you can't put a season on a hazard map with a straight face. And you certainly can't say 9 o'clock in the evening. For that, you needed somebody who was awake that night, on the receiving end, in a society that wrote things down and kept them. Nobody like that existed anywhere near the Pacific Northwest in January 1700. There was somebody about 4,500 miles west, though, on the other side of an ocean, in a country that wrote things down and kept them, and that's where Japan comes in. The village headman at Miho woke up because the sea was behaving oddly. Miho sits on the Izu Peninsula, on a spit of land with a pine grove along the shore and a shrine set back from it. It's a pretty place. It's still a pretty place. You can go. And in the small hours of what his calendar called the 8th day of the 12th month of the 12th year of Genroku, the water started coming up the beach when it had no business coming up the beach. His first thought was that it was a strange run of high tides, which is a very sensible first thought. Tides are what the sea does. But it kept doing it, and it wasn't behaving like tides, and he'd been watching the sea his whole life, and he knew when it was wrong. So he did two things, and I think both of them are the actions of a man I'd quite like to have a drink with. The first thing he did was send the elders and the children up to the shrine, which was on higher ground. Not everyone. Not a panic. He wasn't sure enough for a panic. But he was sure enough to get the people who'd struggled to run out of the way first, on the basis that if he was wrong, they'd have had a chilly walk, and if he was right, they'd be alive. That's not a bad instinct for 4 in the morning with no information. And the second thing he did was stay put and watch. Because he was fascinated. That's the bit that gets me. This man is standing on a beach in the dark in January watching water do something he doesn't understand, and his dominant emotion appears to be curiosity. He watched the pine grove flood. He counted the waves, 7 of them. He noted where the water reached, and then he wrote it all down, in some detail, because it had bothered him, and because he'd noticed something about it that didn't fit. He knew, roughly, what a tsunami was. Japan had been keeping records of earthquakes and tsunamis for something like 14 centuries at that point. It was general knowledge along that coast that when the ground shakes hard, the sea sometimes comes in afterwards. Everybody knew that. It's the sort of thing you'd know without knowing how you knew it. But there had been no earthquake. Not in the village, not nearby, not that anyone had felt. Nothing. The ground had been perfectly still and the sea had come in anyway, and he sat there wondering what you were even supposed to call that. He had no answer. He wrote down the question instead. And that, 300 years later, is the load-bearing sentence of an entire scientific field. He wasn't the only one. That night, the same thing was happening at a string of places up and down the Pacific coast of Honshu, and because this was Edo period Japan, an astonishing number of them wrote it down. Up north in what's now Iwate Prefecture, at Kawagasaki, it was worse than odd. Houses were carried off. And then, because this is the 17th century and every light and every stove in the village is an open flame, the flooding started a fire, and the fire took some of what the water hadn't. That detail stopped me dead the first time I read it. You don't think of flood and fire as a package deal, but of course they are. In a world lit by burning things, the water knocks the lamps over and doesn't reach far enough to put them out. At Tsugaru Ishii records, At Otsuchi, damage to the salt kilns, which were right down at the waterline because that's where you evaporate seawater. Down at Nakaminato in what's now Ibaraki, more of the same. And a very long way south, at Tanabe in Wakayama, the water came into the fields and the crops and got into a government storehouse, and reached a moat by the castle, which astonished the local officials enough that they made a note of exactly where it stopped. 6 places at least, run-up heights of roughly 1.5 to 5 meters depending where you were. Not a catastrophe by Japanese standards. Nobody has ever suggested it was. It was a bad night, some houses went, some fields were ruined, some paperwork got filed, which is precisely why it survived. I want to spend a second on why these records exist, because I think people underrate it, and it's the actual reason we can date this thing. Tokugawa Japan was a paperwork civilization, absolutely obsessed. It had daimyo running domains that ran on rice as currency, which means somebody had to count the rice, which means somebody had to know exactly which fields flooded and how badly, because that changes what the domain can collect. It had land magistrates. It had castle administrators keeping running diaries of anything notable. It had merchants keeping notebooks. It had shrine records. So when a wave comes into a field in 1700, it doesn't vanish into folklore, it goes into a ledger. Because the field is a tax asset, and the wave is a problem for the accounts. The upshot is that a middling coastal nuisance on one night in January got recorded in 6 separate places by 6 separate sets of people, with no idea they were witnessing anything remarkable. And those records were kept, in archives, for 300 years and were still legible when somebody finally went looking. That somebody, in the mid-1990s, was a team led by Kenji Satake, and the method they used is the sort of thing I find deeply satisfying, because it's basically detective work with a stopwatch. Here's the thing about tsunamis. They're not mysterious once they're in the water. A tsunami in the open ocean is a wave in a fluid of known depth, and waves in fluids of known depth travel at a speed you can calculate. The deeper the water, the faster it goes. Since we have very good maps of how deep the Pacific is everywhere, you can model exactly how long a wave takes to get from any point in that ocean to any other point in that ocean. It's just arithmetic, essentially. Very tedious arithmetic, but arithmetic. So if you know when the wave arrived somewhere, you can work backwards to where and when it started. The Japanese records give you the when, small hours, before midnight rolling into the 8th day. Multiple sites, which is even better, because different arrival times at different places let you triangulate rather than guess. Then you go looking for the parent and you do it by elimination. South America, no earthquake recorded on that day. Chile and Peru had Spanish colonial administration by then, and Spanish colonial administration also loved paperwork, and there's nothing. Kamchatka, Alaska, the Aleutians, no records at all, no populations keeping them, but also no wave signature that fits the timing and the sizes, which leaves the northwest coast of North America. The one stretch of the Pacific Rim that in January 1700 had no written records whatsoever, no European charts, nothing. The outside world barely knew that coastline existed. There's a French map from 1720, 20 years later, that's still basically guessing at the shape of it. That's where the wave came from. Satake's team published it in 1996, and it's one of those results that reframes everything around it. Cascadia had been fingered by a tsunami that arrived in a country 4,500 miles away and left evidence in a tax ledger. There's a calendar problem in the middle of all this, and I want to touch on it because it's the sort of thing that gets waved away and is actually load-bearing. Japan in 1700 was not using the calendar we use. Genroku 12, 12th month, 8th day, is a date in a lunar-solar system, tied to eras that get renamed when something significant happens, with months that track the moon and leap months shoved in periodically to stop the whole thing drifting away from the seasons. So converting that to the 27th of January, 1700 isn't a lookup, it's a proper piece of scholarship. You need to know the era, the intercalation rules, which years had leap months, and you need to trust that the person writing the entry was using the same conventions as everyone else, which was not always a safe assumption. That work exists, and it's solid, and it's one of the reasons the team on this was as large and as mixed as it was. There were Japanese historians on that project, not as translators, as investigators. Satoko Musumi Rokaku, Yoshinobu Tsuji, Kazue Ueda. You cannot do this with a geologist and a dictionary. Somebody has to be able to read Edo period administrative handwriting and know what a domain diary is and know which archive it's sitting in. The other thing the records give you, apart from the timing, is a size, because the run-up heights are in there. How far up the beach it came, what it flooded, where exactly it stopped in relation to a moat that is, helpfully, still there. And a wave height at a known distance from a known source is a constraint on how big the source was. The bigger the rupture, the more seafloor gets shoved, the more water gets displaced, the bigger the wave that arrives 4,500 miles away. So you run the model backwards. You try a magnitude 8 source, see what arrives in Iwate and it's too small. You try a 9.5 and it's far too big. The records would describe a catastrophe and they describe a bad night. You keep going until the modelled wave matches what 6 separate villages wrote down. The answer that falls out is somewhere between magnitude 8.7 and 9.2. That's where the number in the title comes from. Not from an instrument, from matching a computer model of an ocean against the recorded height of water in a Japanese rice field, 3 centuries after the water went home. I think that's about as clever as science gets, honestly, and it explains why nobody says magnitude 9.0 flat if they're being careful. It's a range. The middle of the range is roughly 9, and roughly 9 is what everyone says, but the honest version has a spread on it. There's one more layer to this that's genuinely difficult, and Atwater and his co-authors put it in the 2nd edition of the book they wrote about all this. In March 2011, a magnitude 9 ruptured off Tohoku, on the Japanese side, and sent a tsunami across the Pacific in the other direction. Same ocean, same crossing, opposite ends. The waves that reached the coast of Oregon and Washington in 2011 were, in the most literal sense available, the mirror image of the ones that went the other way in 1700. Japan spent 300 years holding the evidence of Cascadia's earthquake, and then Cascadia spent an afternoon receiving the evidence of Japan's. I don't have anything clever to say about that. It's just true, and it sat with me for a while. And then the last step, which is the one that gives us the hour. The crossing takes about 9 hours. That's the model, and it's calibrated against modern tsunamis where we know both ends of the journey precisely because unfortunately we have several to check against. 9 hours from Cascadia to Honshu. The Japanese records put the wave arriving before midnight on the 27th of January. Subtract 9. You land at about 9 o'clock in the evening on the 26th of January 1700 on the coast of what is now Washington and Oregon and British Columbia. That's it. That's the whole trick. The trees gave us the winter, the ledgers gave us the evening, and between them they gave us a magnitude 9 earthquake with a date and a rough hour on it, from a place and a time with no clocks and no calendars, and nobody writing anything down. The name comes from that headman's problem. A tsunami with no earthquake in front of it is a wave with no parent. In Japan, it was an orphan. It had been an orphan for very nearly 300 years before anyone worked out where it had come from, and I quite like the idea that the reunion took that long and was arranged in the end by dead trees. The reason it stayed unsolved so long is not that it was hard exactly. It's that nobody had any reason to look. Why would you? If you're a Japanese seismologist in 1950 with an unexplained wave in your catalogue, the last thing on your list of suspects is a fault on the other side of the world that the entire profession has agreed is inert. You need somebody to suggest the fault might not be inert first, and that took a man in a marsh with a hand hoe in 1986, which is a full 286 years after the headman at Miho stood on his beach, counting waves in the dark and wondering what to write. I want to pick a small fight with a word, and it's a word I've probably used myself a few times already tonight without thinking about it. The word is discovered. You'll read, in a lot of otherwise excellent writing about this, that the 1700 Cascadia earthquake was discovered in the 1980s, and every time I see that sentence I stop, because it's such a strange thing to say about an event that had been in continuous circulation as a story for something like 300 years without a break. It wasn't discovered, it was, at best, confirmed, by people who had not been listening, from people who had been telling them the whole time. Let me be careful here, because I don't want to do the opposite silly thing either. The tree rings and the ledgers gave us a date and an hour and a magnitude, and no oral tradition anywhere gives you those, and I'm not going to pretend otherwise. Different tools do different jobs. But the fault's most recent rupture was never actually unknown. It was unknown to a specific profession, in a specific century, that had decided in advance which kinds of information counted. And there's a detail in this that I only noticed on about the 4th pass through my notes, and once I'd seen it I couldn't stop seeing it. Near Bay, the beach where Atwater knelt down with the hand hoe and found the arrow grass. That's Maka land. That's the Maka reservation, right up on the corner of the continent, and the Makar are one of the peoples whose accounts Ludwin catalogued. So the man who went out to look for the first physical evidence that the fault had ever ruptured went and dug on the beach of a community that had been carrying the account of that rupture the entire time. He found it in the mud roughly a metre under a place where the answer had been in continuous circulation, out loud, in the air, for 300 years. I'm not making a point about anyone's competence. Atwater was doing careful, brilliant work, and by all accounts he was aware of the traditions and took them seriously as a reason to go looking in the first place. That's actually why it's such a good story. The story's pointed, and somebody listened and went and dug where they were pointing. But the geography of it is quite something. The evidence was underground, and the testimony was overground, and they were in the same place. So, along that coast, from Northern California to the top end of Vancouver Island, there are stories about Thunderbird and whale. They're not all the same story. That's the first thing to say, because it gets flattened a lot. There are versions among the Yurok and the Tolowa in Northern California, the Tillamook and the Siletz in Oregon, the Quileute, the Quinault, the Hoh, the Makah and the Lummi in Washington, the Huayat, the Hesquiat, the wider Nucha-Nulth, the Kwakwakawaku on Vancouver Island. Dozens of communities, many different languages, their own traditions, their own contexts. What they share is a shape, and the shape, roughly, is a fight. An enormous bird and an enormous whale locked together, and the fight is so violent that the land shakes and the sea comes up over it. The easy read on that is, nice myth, moving on. And that read is wrong, and the person who did the most to show why is a seismologist called Ruth Ludwin, who went through these accounts with her colleagues and published on them in 2005. Her argument, and I think it's a genuinely important one, is that you have to look at how these stories are constructed. They use symbolism and they use memory devices. Rhyme, structure, repetition, concrete images. The kind of scaffolding that exists specifically so that information survives being passed from a person to a person to a person for centuries without a single copy of it being written down. That's not decoration. That's engineering. If you have no writing and you need a fact to survive 12 generations, you don't tell people a fact. Facts don't survive 12 generations. You build the fact into something with hooks on it. And once you read them that way, the accounts stop being vague and start being specific in a way that's a bit unnerving. In one version, Thunderbird drives its talons into whale's back, and whale dives and drags Thunderbird down to the bottom of the ocean with it. Read that as an image, and it's mythology. Read it as a description of a sequence of events, and it's ground shaking followed by the ocean surging over the land. That's the order. That's what actually happens. The shaking comes first, and the water follows. But the account I keep coming back to isn't a Thunderbird story at all. It's much plainer and much worse. In 1964, an ethnographer called Eugenia Riemer was recording oral histories with Huayat elders on Vancouver Island, and a Huayat man named Louis Clamhouse told him what had happened at Pachena Bay. Pachena Bay is on the southwest coast of the island. It's a beautiful spot, a wide sandy bay opening straight onto the Pacific. There was a winter village there. That's where people lived in the cold months, because winter villages went in sheltered places near the water, where you could get at food and pull the canoes up. The account, which comes to us through Chief Louis Nookmis, is that the land shook at night, and then a wave came out of the dark, and everyone living at Pachena Bay was lost. Everyone. There's no softening in it. People didn't get out. They didn't have time to wake up properly and get to the canoes. The account describes everything drifting away, everything lost and gone. The only people who came through it were at a place called Maltzus. It translates as house up against hill. It's exactly what it sounds like. It's higher up, and the reason they survived, the account says plainly, is that they did not drift out to sea with the others. That's the whole difference. Elevation. That's it. That's the entire mechanism of survival and death that night, recorded in a name. There's a threshold in these accounts, and it's a horrible one. In the low-lying settlements, below about 75 feet above the sea, there were no survivors. Above it, people lived. A hillside is the difference. And there's another detail in the Coast Salish and Nucha-Nulth accounts that I think is the single most physically specific thing in the entire evidence base for this earthquake, from any source, of any kind. They describe shaking so violent that people could not stand up, and they describe it lasting so long that it made them seasick. Sit with that for a second. Seasick. That's not a metaphor anyone would reach for casually. Seasickness is a very particular thing. It happens when your inner ear and your eyes disagree about whether you're moving, and it takes sustained, rolling, repetitive motion to bring it on. You do not get seasick in 10 seconds. You do not get seasick from a jolt. You get seasick from minutes of it. Minutes of the ground moving like water underneath you. There is no instrument reading from 1700. There's no seismogram. There's no accelerometer. This single best description we have of what the shaking actually felt like, in a human body in the dark, comes from an oral account passed down through generations of people whose ancestors were standing in it. And it agrees with the physics. We'll get to why the shaking lasted that long in a bit, but it did, and they said it did, and nobody was checking their work. And Pachena Bay is the most specific account, but it's very far from the only one, and I think the range of them is worth sitting with because the range is the argument. Down in Washington, the Quileute and the Ho describe Thunderbird and Whale having a terrible fight that shook the mountains and pulled the trees up by the roots, and the ocean rising and covering the land. That's two distinct hazards in one sentence, in the right order. On Vancouver Island, there's a Nucha Nulth account that's much stranger, and once you look at it properly, quite funny in a very dark way. Dwarfs living inside a mountain invite a man to dance around their drum. He kicks the drum by accident, and from then on he has earthquake foot, and every step he takes makes the ground shake. As a story, that's charming. As a piece of encoding, it's doing something rather elegant, which is attaching the shaking to a mountain and to an accident, and to a person who now carries it around, all of which are hooks. You can hang information on a man with earthquake foot. You cannot hang information on the sentence, "The ground shakes sometimes." Further south in Oregon, there are accounts collected much later that carry the same shape. Annie Miner Peterson, speaking in 1910 about southern Oregon, described her grandfather having seen one of the old women who had survived. Not a myth. A person. Somebody's grandfather met somebody who lived through it, and that got carried forward and written down. There's an unidentified account from around 1860 describing a tide that came up at a fearful speed, which is not what tides do, and is very much what the near-field wave does. And when Robert Dennis, who became chief counselor of the Hu-Ayat, was a boy of 11 or 12, his great-grandfather used to tell him things, not stories for entertainment. He framed them explicitly as things that might matter in his life, and as things that could happen again. One of them was about Pachena Bay, the land shaking, the wave, the people on the bay all lost, and the people on high ground coming through it. That's the transmission mechanism right there, described from the inside. An old man telling a child something on purpose, with a stated reason, because the child will one day be the one who has to know it. Ludwin's catalogue pulled together dozens of these, and part of what makes it convincing is that they don't all agree. If they were all identical, you'd suspect a single source copied around. They're not. They're different peoples, different languages, different framings, some mythological and some flatly literal, some with a bird and some with dwarfs and some with nothing but a description of a night. What they share is a coastline, a sequence, and a survival rule. There's an archaeological angle in there too. Artifacts along the coast tied to the Thunderbird and Whale tradition imply the stories were around before 1700, which would mean the tradition isn't a record of one night. It's a record of a recurring event, which fits, because it is one. There's a dating angle too, which I find quietly remarkable. Some of these accounts come with generation counts attached. So-and-so's great-great-grandfather, that far back, that many people ago. And when you take those counts and do the arithmetic on typical generation lengths, you land in a window somewhere between about 1640 and 1740. That's rougher than the tree rings, obviously. A 100-year window is not an evening. But it was arrived at completely independently by an entirely different method, using no physical evidence whatsoever, and it contains the right answer. The stories and the would agree, and neither of them was consulting the other. Here's where it ends up, and I think it's the right place for it to end up. If you go and read the current United States Geological Survey material on Cascadia megathrust earthquakes, the bit where they lay out the evidence base, you'll find indigenous oral histories listed in there, not in a sidebar, not as colour, in the paragraph, alongside the turbidites and the tsunami deposits and the dendrochronology, as a line of evidence for great earthquakes in Cascadia. That took a long time, and it should not have taken a long time, but it's there. And then there's the thing the Hu-Ayat did, which is my favourite footnote in this whole story. When they built their new administration building, they put it high above Pachena Bay, on the advice of their elders, because the elders knew what had happened there, and knew it could happen again, and said so. which means the information did its job. That's what it was for. It was built with hooks on it so it would survive 300 years and 12 generations and arrive in a meeting about a building site still legible, still load-bearing, still correct. They've got a nice view from up there, apparently. Everything I'm about to tell you in this section is inferred. I want to get that out of the way at the top, because this is the part of the story where it's easiest to start narrating like there was a camera crew present and there wasn't. There was no seismometer. There was no tide gauge. There was nobody keeping a log. What we have is a set of consequences scattered across an ocean and a coastline, and a physical understanding of what kind of event produces consequences like that. So none of the numbers coming up are measurements. They're all reconstructions. Well-founded ones, with a lot of work behind them, but reconstructions. I'd rather say that than pretend to a precision nobody has. Right. With that on the record. The rupture ran along most of 1,000 kilometers of fault. That's the working picture. From somewhere around the middle of Vancouver Island down to somewhere around Cape Mendocino in Northern California, give or take at both ends, which is a genuinely contested question we'll come to later on. But call it 1,000 kilometers of fault surface that had been stuck, coming unstuck. And the way it comes unstuck is the part that explains everything else. So let's do that properly. A fault doesn't let go everywhere at once. It can't. Nothing that big is that coordinated. What actually happens is that it fails at one spot, somewhere the friction was weakest or the strain was highest, and then that failure spreads. The rock next door, which was already holding as much strain as it could manage, suddenly has its neighbour stop helping, and so it goes too, and then its neighbour goes, and off it runs. It unzips. That's the word people use, and it's a good one. The rupture front travels along the fault like a zip coming undone, and it does it at roughly 2 kilometers a second. 2 kilometers a second sounds fast, and it is fast. It's about the speed of a rifle round. But look at the sum. 1,000 kilometers at 2 kilometers a second is 500 seconds. That's your 5 minutes. Right there. That's where the number comes from, and it isn't a guess about how bad it felt. It's arithmetic about how long the zip takes to run. And this is the thing about megathrust earthquakes that I don't think lands properly until you say it out loud. So let me say it out loud. Most damaging earthquakes last 10 to 30 seconds. That's the real range for the kind of event that flattens a town. 10 seconds, 30 at the outside. The 1994 Northridge quake, which did about $20 billion of damage, was in that range. Most of what you've seen footage of is in that range. 5 minutes is not a bigger version of that. It's a different category of experience. 30 seconds is something that happens to you. 5 minutes is a situation you're inside of, with time to notice what's happening and react, and have the reaction fail and try something else and have that fail too, all while it continues. Which brings us straight back to the seasickness, and I'll leave that where it is because we've already done it, but the two things fit together exactly. Of course it made people seasick. It went on for 5 minutes. The second thing that happens in that same 5 minutes, the coast drops, 1 to 2 meters, straight down, permanently, for the reasons we went through with the marshes and the cedars. Doesn't happen after the shaking, it happens during. The subsidence and the rupture are the same event. So a person standing on that coast at 9 in the evening in the dark in January is experiencing 5 minutes of ground moving like a boat deck. And in the middle of it, the entire place they're standing on quietly loses a meter or two of elevation, without anybody being able to perceive that as a separate thing. You wouldn't feel it. There's no reference point. You'd only find out later when the tide came in further than it should. And then, the third thing, a rupture that size shoves the seafloor, not gently. The upper plate, which has been bent and held down for centuries, springs back, and it does that under a very large volume of water, and the water has to go somewhere. It goes 2 directions at once. That's the bit people miss. Half of it goes west out into the open Pacific and starts the long crossing we've already talked about, arriving in Japan while everybody involved is asleep, and half of it goes east, straight at the coast that's just been shaken for 5 minutes and then dropped a meter or two. The near-field wave doesn't take hours. The fault is barely 100 kilometers offshore. The wave arrives in minutes, somewhere in the region of 20 to 30 minutes depending where you are. That's the entire window. That's it. Between the shaking stopping and the water arriving, at some places on that coast, is about the length of a sitcom episode. And the ground has just gone down, so the water comes in further than the same wave would have managed the day before. The two effects stack. It's a genuinely nasty piece of engineering. There's a geographical mercy in all this that gets buried under the headlines, and I want to give it its due because it's real. The fault is offshore. That sounds obvious, but the consequences aren't. The strongest shaking in an earthquake is nearest the rupture, and the rupture is out under the sea, 100-odd kilometres from the coast, and considerably further from the cities. Energy drops off with distance, so Seattle and Portland, which is where nearly everybody actually lives, are not sitting on top of the thing, they're sitting a good way inland from it. That's why you'll find Canadian seismologists making a point that surprises people, which is that the megathrust is not actually the biggest earthquake hazard facing the major cities of that coast. The shallow faults directly underneath the cities are, because they're much closer even though they're much smaller. There have been several magnitude 7s in the southwest of British Columbia and northern Washington in the last century and a bit, and a moderate earthquake directly under your feet can do more to your particular building than an enormous 1-200 kilometres away. So the picture isn't one uniform apocalypse, it's a gradient. The coast gets the full experience, shaking and drop and water in that order, with minutes between them. The inland valleys get a long, rolling, deeply unpleasant few minutes, and then infrastructure problems for a year. Those are very different days. The coverage tends to blur them into one, which is how you get the impression that 7 million people are all in the same boat. They're not. They're in about 4 different boats, and only one of them is near the water. A word about magnitude, since I've been throwing the number around all night and I've never actually explained what it means, which is a bit rude of me. The scale is logarithmic, which everyone says and almost nobody unpacks. What it means practically is that each whole step up is about 32 times more energy released. Not 32%, 32 times. So a magnitude 8 isn't a slightly bigger 7, it's about 32 7s, and a 9 is about 32 8s, which is around 1,000 7s. Which is why the San Andreas comparison is a bit unfair to the San Andreas. Every fault has a ceiling, and the ceiling is set by geometry, by how long the fault is, and how wide the slipping surface can be and how far it can move. The San Andreas is a very long fault, but it's a relatively narrow one, because it's a vertical crack, and there's only so much depth available before the rock gets too hot and soft to snap. So its ceiling is somewhere around 8.2, and that's not a slight, that's an enormous earthquake. It's just not in the same category. A megathrust is a shallow angled sheet. It's not a crack, it's a ramp. Which means the slipping surface isn't a narrow ribbon going down, it's a wide plane going out, 100 kilometres across in places. Long times wide gives you area, and area is what makes magnitude, and a fault with that much area available has a much, much higher ceiling. That's the whole difference. It's not that Cascadia is angrier, it's that it's got more room. The other thing worth mentioning, because it does a lot of the damage and nobody talks about it, is liquefaction. Shake wet sandy ground for long enough, and it stops behaving like ground. The grains, which were resting on each other and holding everything up, get jostled apart, and the water between them takes the weight instead, and water cannot take weight. So the soil turns, briefly, into something with the mechanical properties of a thick soup. Buildings sink into it, buried tanks float up out of it, roads go wavy, and the key variable in liquefaction is duration. It takes sustained shaking to get there. 30 seconds often isn't enough. 5 minutes is comfortably enough, which is the second time tonight that the 5 minutes turns out to be the thing that matters rather than the intensity. Long is worse than hard for a lot of failure mechanisms. Long is what breaks things that would have survived hard. As for the wave itself, the estimates for what a full margin rupture can throw at that coastline run frighteningly high. Oregon's own emergency management people talk about tsunami heights of up to 100 feet reaching the coast in the worst spots, with the state's resilience work putting the highest waves around 80. Those are extremes at particular places where the shape of a bay funnels and stacks the water. Most of the coast doesn't get that, but some of it does, and where the water goes is mostly a question of the shape of the ground, which is why the maps are so patchy and specific, and why a town can be fine and the next bay along can be gone. What was actually there, on that coast, on that evening? It was winter, late January, so people were in winter villages, which is exactly what it sounds like. The settlements you move to for the cold half of the year, and they tended to be in the sheltered spots, bays, river mouths, the lee side of a headland, near the water, because everything you eat comes out of the water, and because you need the canoes accessible, which is to say, the places that were good to live in winter and the places the wave would reach were substantially the same places. That's not a mistake anybody made. It's just what a coastline is. You live where the living is good, and the living is good near the water, cedar plank houses, Big ones, some of them, communal, built to last. Canoes pulled up, fires going because January. 9 in the evening, so not everyone asleep, but the day's over, and then 5 minutes, and then the dark, and then the water. Here's a small thing that I find quietly dislocating, and I'll offer it without dressing it up. The 26th of January, 1700 was a Tuesday. For essentially everybody else on the planet, it was a Tuesday and nothing happened. Someone in London had a Tuesday. Someone in Beijing had a Tuesday. The Japanese coast was about 9 hours away from having a slightly odd Wednesday morning and didn't know it yet. And on one coastline, out of contact with all of it, the largest earthquake in the recorded history of North America was happening in the dark to people whose descendants would still be telling us about it 3 centuries later. Nobody sent word because there was nobody to send word to and no way to send it. The event simply happened, entirely locally, to the people it happened to, and the rest of the world's Tuesday continued. And then, of course, it isn't finished, because these things never finish neatly. A rupture that size doesn't stop and go quiet. It rearranges the stress in an enormous volume of rock, and all that rock has to settle into the new arrangement, and settling is aftershocks. Not a few, months of them. Some of them large enough that in any other week they'd be the main event. So the night of the 26th isn't a night, really. It's the start of a season. Ground that's already been shaken for 5 minutes and dropped a metre, getting hit again and again through the winter, while everybody's living in whatever's left in January, on a coast where all the food comes out of a sea that has just been thoroughly rearranged. The winter after is not something the evidence has much to say about. But it happened to somebody, which leads to the honest limit of this section, and I'd rather end on it than dodge it. We will never have a casualty figure, not an estimate, not a range, nothing. There's no census, there's no roll. The record we have is a set of buried marshes, a stand of dead trees, some tax paperwork in Iwate, and a body of oral accounts that tell us specific villages were entirely lost, without telling us how many people were in them, because that was never the point of the telling. Every other number in this video is an inference from physics. That one isn't available at any price. The most human fact about the whole event is the only one the evidence has nothing to say about. I don't think there's a fix for that. It's just how it is. But I'd rather leave the gap visible than fill it with something I made up. Mud. That's this section. Underwater landslide mud specifically, and I appreciate that's not an obvious sell at this point in the evening. The mud is how we know this isn't a one-off. So, off the edge of the continent, where the shallow shelf drops away into deep water, there's a slope. And sitting on that slope is sediment. Everything the rivers of the Pacific Northwest have carried down and dumped over the edge for thousands of years. Silt, sand, the lot, piled up in a way that is, frankly, precarious. It's held there by nothing more than friction and its own reluctance. Shake it hard enough and it goes. The whole lot slides off the slope at once and pours down into the deep basins below in an enormous underwater avalanche of muddy water. That's called a turbidity current, and the deposit it leaves at the bottom is called a turbidite. And turbidites have a shape. That's what makes them useful. When the avalanche stops moving, the sediment settles out of the water in order of weight. Coarse sand goes down first because it's heavy, then finer sand, then silt. Then the really fine stuff drifts down over hours and days on top of everything, so you get a layer that's gritty at the bottom and gets progressively finer all the way up, capped with a lid of fine mud. That's a signature. You can't get that shape from ordinary sedimentation. Ordinary sedimentation just quietly rains down, year after year, at a boring constant rate. A turbidite is a violent interruption in a boring record, and it looks completely different from the boring bits either side of it. So you take a core, you drop a tube into the seafloor, pull up a column of sediment, and read it from the bottom up. Boring mud, boring mud, boring mud, then bang, a graded layer. Then more boring mud, then bang, another one. It's a ledger. Every entry is a day something enormous shook the continental slope, and the boring mud in between is the clock, because it accumulates at a rate you can work out, so the thickness between two events tells you roughly how much time passed. Chris Goldfinger has spent decades on this, and the count that came out of that work is 41. 41 subduction zone events of varying size along the Cascadia margin over roughly the last 10,000 years, read out of the mud. Of those, the ones big enough to have ruptured along most of the coastline, the genuinely great ones, magnitude 8 and above, number at least 19. 19. Over 10,000 years. And the most recent one is the one we've spent the whole night on. Something surprised me here, and I think it's properly funny. Cascadia is, by a distance, the best documented subduction zone on Earth for this kind of long record work. The most paleoseismically well-constrained one on the planet. Better than Japan. Better than Chile. Better than Alaska. The quiet one. Which is the same joke the whole subject keeps telling, and I won't labour it twice. No instrumental record meant everyone had to go and read mud instead, and mud goes back 10,000 years. A small revenge. And it's not one method either, which is the actual reason it's so solid. You've got the coastal subsidence in the buried marshes. You've got tsunami sand deposits thrown inland over the marsh and left there. You've got the turbidites offshore. You've got turbidites in inland lakes from the same shaking. You've got landslide deposits. You've got liquefaction features. You've got the tree rings. You've got the Japanese records for the most recent one. And you've got the oral histories. 9 independent lines of evidence from geology, botany, archives and testimony, all pointing at the same set of events. That's why it's not really arguable anymore. You'd have to be wrong about all of them in the same direction by coincidence. There's a lovely piece of machinery underneath the turbidite work that I want to show you, because otherwise it sounds like people are just counting stripes and hoping. The problem with reading mud is that mud is not a clock face. You've got a core with layers in it, and you need to know how old each layer is, and the boring mud accumulation rate trick gets you an estimate, but it drifts, because accumulation rates change. So what you really want is a marker, a layer that you know the date of, that shows up in every core, that you can anchor everything else to. And in the Pacific Northwest there's a beauty. About 7,500 years ago, the volcano we now call Mount Mazama erupted catastrophically and blew its own summit off, and what's left of the hole is Crater Lake. It was an enormous event, and it put a layer of distinctive ash over an absolutely vast area, including out onto the seafloor, so there it is, in the cores. A dated, unmistakable, region-wide line. Everything above it is younger than that, everything below is older, and it's the same line in every core from every basin, which means you can correlate. You can take a core from off the coast of Washington and a core from off the coast of Oregon, find the ash in both, and start counting turbidites up from it in each one, and see whether the events line up. If a turbidite in Washington and a turbidite in Oregon sit the same distance above the ash, with the same amount of mud in between, that's an argument that they're the same event, which is an argument that the rupture ran through both places. That's how you get from stripes in a tube to a rupture length. It's the ash that lets you do it. Goldfinger found 13 earthquakes worth of turbidites since the Mazama ash, and 18 going back to the start of the Holocene, which is roughly 10,000 years, and those numbers are the backbone of the whole margin-wide picture. The number everyone wants, and then the reason the number is a bit of a trap. Average recurrence for a full margin rupture, the whole thing going at once, is about 500 years. That's the figure the National Hazard Model uses, and it's what you'll see quoted more or less everywhere. 500 years, last one was 1700, do the sum, and now let me take the average away from you, because I don't think it deserves the confidence people give it. The actual intervals in that record run from about 200 years to about 800 years. 200 to 800, that's the real spread, and an average of a set that's spread out is a number that describes nothing that ever happened. It's a summary that summarizes nothing. If I tell you the average gap is 500 years, you picture a fault that goes off every 500 years, plus or minus a bit, and that fault does not exist. That's not what's in the mud. We saw a version of this earlier with the buried marshes, where 3 events landed inside a 500-year window at one site, and 900 years went by between 2 others. Same story, different evidence. And down in the Sixes River estuary in southern Oregon, Harvey Kelsey, Eileen Hemphill-Haley and their colleagues found 11 earthquakes in 5,500 years, with the gaps between them running from about 70 years to as much as 900. 70 years. Somewhere in that record is a generation that got 2 of these. Their parents lived through one and they lived through the next one. So the fault has a rate, but it doesn't have a rhythm. It has a distribution. Which is a much less satisfying thing to say, and considerably more honest. The live argument, and I want to present it as live because it is. In June of 2024, a team published the first proper comprehensive survey of the structures under the seafloor along nearly the whole zone. Research vessel, towed array of instruments, the works. And what came out of it is that the megathrust doesn't look like one continuous thing. It looks like at least 4 segments. Distinct chunks, with real geological boundaries between them, and the suggestion is that each one may be somewhat insulated from what the others are doing. A rupture that gets going in one segment might not automatically carry through into the next, which reopens a question that has never really been closed, and it's this. Did 1700 rupture the whole margin, or did it rupture part of it? Because everything we've said tonight, the 1,000 kilometres, the 5 minutes, the magnitude 9, hangs on the full margin picture. If the whole thing went at once, that's what you get. If it didn't, if it was a large rupture on part of the fault, the numbers come down, and it's kept going since. In early 2026, another study came out using seismic noise, which is a phrase I want to dwell on for a moment because it's such a good idea. Seismic noise is the constant faint background rumble of the planet, waves hitting coastlines, wind, traffic, the lot. It's the stuff seismologists spent decades trying to filter out as rubbish. And it turns out that if you're clever about it, the rubbish is data, because it's energy passing through the rock, and it comes out the other side carrying information about what it went through. What that work suggested is that the fault has more variety in it than the tidy locked everywhere picture implied. There's evidence for fluids moving up through the structure along what amount to plumbing routes, and there's a suggestion that the central part of the zone may not be as fully locked as the northern part, which would mean it isn't accumulating strain at the same rate as its neighbours. I'd hold that loosely. It's recent, it's being argued about, and the interpretation isn't settled. But it points the same way as the segmentation work, which is that this fault is less uniform than a diagram makes it look, and the diagram has been doing a lot of quiet work in everyone's imagination for 40 years. The evidence points at the big version. The trees died at the same time across a long stretch of coast. The Japanese wave was large enough and arrived in a pattern that fits a very big source. It hangs together. But it's not settled, and I'd rather tell you that than hand you a certainty nobody has. What the segmentation does do is give you a second category of event, and that changes the maths in a way that matters for the last section. Full margin ruptures, the everything at once magnitude 9 kind, run at roughly the 500-year rate. Partial ruptures, where only a chunk goes, might run every 800 to 1,000 years down in southern Cascadia. Stack those two together, and you get something like a great earthquake, magnitude 8 or bigger, at any given site in southern Cascadia roughly every 3 to 3.5 centuries, which is a different question to how often the whole fault goes off, and the two get muddled constantly in the coverage, and the muddling is where a lot of the scarier headlines come from. There's an entire video in the turbidite argument alone, honestly. And since I've been leaning on it all section, I should at least tell you where the soft ground is. The objection goes roughly like this. A turbidite tells you the continental slope let go. It does not tell you why, and there are other things that can shake sediment off a slope, or just make it fall off on its own. Storms, a big enough river flood, the slope simply getting overloaded and giving way because that's what precarious piles of sediment eventually do, so how confident can you be that a given layer is an earthquake rather than a Tuesday? The answer, and I think it's a decent one, is in the correlation. A storm is local, a slope collapse is local. If a layer shows up in one basin, shrug. If the same layer, at the same level with the same amount of boring mud under it, shows up in basins hundreds of kilometres apart, then whatever caused it was hundreds of kilometres wide, and the list of things that are hundreds of kilometres wide and shake the seafloor is short. The counter to the counter is that correlating layers between distant cores is a judgment call done by people who already believe there was an earthquake, and that's the kind of setup where you find what you expect. That's a fair worry. It's the sort of thing that keeps honest people up at night, and it should. So there's a live argument about whether some of the events in that count are one earthquake read twice, or two earthquakes smeared into one, and about how precise the correlations really are. Good people on both sides. I've barely gestured at it here. Might do that one properly sometime. For tonight, it comes down to this. The fault has done this at least 19 times that we can see. It does it irregularly, and the mud is the only reason anybody knows either of those things. I've got a problem with a word, and I'm going to say it once and then let it go. Overdue. You see it everywhere with this fault. Cascadia is overdue. The big one is overdue. It's the framing that basically all the coverage reaches for, and I don't think it means anything, and I think it actively makes people worse at thinking about this. Here's why. Overdue implies a schedule. It implies something that was supposed to arrive and hasn't, and is therefore more likely to arrive imminently because it's running late. That's how buses work. It is not how faults work. The standard way of computing these probabilities treats earthquakes as having no memory at all. The fault doesn't know what year it is. It doesn't know 1700 happened. It has no calendar, no expectations, and no sense of being behind. It has strain and a friction threshold, and when one exceeds the other it goes. That's the whole of its inner life. And even if you do use a model with memory, which is a perfectly reasonable thing to do and we'll get to it, look at what we established with the mud. Intervals of 200 to 800 years. We're 326 years past 1700. 326 is not late. Given the spread we went through with the mud, it's sitting mid-range. It's not a debt. Nobody's owed anything. The actual numbers, and I'm going to give them to you once, plainly, and then not repeat them at you all night. The United States Geological Survey published the current figures in a fact sheet in 2025, and they run like this. If you assume no memory, the pure no calendar version, the chance of another magnitude 9 on Cascadia in the next 50 years is about 10%. If you use the model that does account for the fact that 1700 already happened and strain has been rebuilding since, that goes up to about 15%. And if you ask a slightly different question, which is the chance of a magnitude 8 or bigger in southern Cascadia specifically, taking in both the full margin and the partial ruptures we talked about, that comes out around 30%. 50 years in each case. 50 years being roughly the design life of a building, which is why they use it. It's not a prediction about you, it's a number for a structural engineer. So what does that actually feel like? 15% over 50 years is genuinely difficult to hold in your head, because it's in the dead zone. It's too high to laugh off and too low to organise your life around, and human beings are famously rubbish at exactly that band. It's roughly the odds of rolling a 6 on a die. Once. Over half a century. You wouldn't bet your house on it landing. You also wouldn't bet your house on it not landing. If somebody told you there was that sort of chance your roof would come off at some point in the next 50 years, you wouldn't move out. You'd probably have a look at the roof. That's the correct response, and it's the response almost nobody has, because our brains only really have two settings for this, which are ignore it and panic, and neither of them is available in that band. Now the uncomfortable bit, which I'd rather say than skip. There's no warning sign. That's not a dramatic statement, it's a straightforward statement of where the science currently is. In Japan and in Chile, slow slip of the sort we mentioned right at the start has been observed running up to megathrust earthquakes. So there's a hypothesis that the quiet creeping might sometimes be a prelude. In Cascadia, that link is not known to exist. It happens on schedule, it's been happening the whole time anyone's been watching, and nobody has established any relationship between it and the big event. So it isn't a countdown, it's just a thing the fault does. Which means, as of tonight, there is no identified precursor, nothing to watch for. The first indication that it's happening will be that it's happening. I don't like that, and I'm not going to pretend the discomfort away. It's just true. So, the coast it would land on. West of Interstate 5, in the Pacific Northwest, there are around 7 million people. That's Seattle, Tacoma, Portland, Eugene, Salem, Olympia, the two state capitals and most of the population of the region. The line everybody knows came from Kenneth Murphy, who ran the Federal Emergency Management Agency's regional division covering Oregon, Washington, Idaho, and Alaska. Talking about a full margin rupture, he said the operating assumption is that everything west of Interstate 5 will be toast. That sentence has done more to shape how the Pacific Northwest feels about this fault than every scientific paper about it combined. It went round the world in 2015 in a New Yorker piece by Catherine Schultz that won a Pulitzer, and I understand entirely why it travelled. It's a hell of a sentence. It's also, as the seismologist pointed out fairly quickly afterwards, a bit of internal agency shorthand for planning purposes that was never designed to be read as a forecast of universal destruction. The federal projection for deaths in a full margin event is somewhere around 13,000, which is a horrifying number, and is also, I think, worth noting plainly, not everyone. It's not a region erased. 7 million people live there, and the projection is 13,000. Both of those facts are true simultaneously, and the second one gets lost constantly. The reason the projections are as ugly as they are isn't really the fault, though. It's the buildings. And the timeline on the buildings is the single most frustrating fact in this entire subject. Oregon had no seismic building code at all until 1974. None. You could build whatever you liked, in a state sitting on a megathrust and nobody was going to stop you. And a code appropriate to a magnitude 9, the sort that assumes minutes rather than seconds and designs for it, didn't really arrive in the Pacific Northwest until 1994, which is, if you're keeping track, 7 years after Atwater published. It took the better part of a decade for a discovery about the ground to make it into the rules about what you're allowed to put on the ground, and honestly 7 years is quite good going for that particular journey. But look at what it means. The vast majority of buildings in that region went up before anyone knew, not before anyone cared. Before anyone knew. There was no negligence involved, there was simply no information. Ian Madden, who ran Oregon's geology department, has put the figure at around 75% of all structures in the state not designed to withstand a major Cascadia quake. Federal modelling has something on the order of 1 million buildings across the region collapsing or being compromised. More than 3,000 of them schools, half of all highway bridges, 15 of the 17 bridges over Portland's 2 rivers, 2/3 of the railways and airports, 1/3 of fire stations, half of police stations, 2/3 of hospitals. That last cluster is the one that gets me, the fire stations and the hospitals, because those are the buildings whose entire job begins the moment everything else stops working, and a meaningful fraction of them are expected to be part of the problem rather than the solution. None of which is anyone's fault exactly. It's just the accumulated weight of a century of building on a coastline that everybody had been assured was geologically dull. The part I actually wanted to get to is newer, and it's the thing I found most interesting in the modern research. Everyone focuses on the shaking and the wave. 5 minutes, then the water, then it's over and you rebuild. Except it isn't over, because of the drop. Tina Dura and her colleagues published work on this in 2025, and what they did was model the subsidence properly. The same mechanism we spent all that time on with the cedars and the marshes, except aimed forwards instead of backwards. Their range for the next one is a coastal drop of somewhere between about 1.5 and 6.5 feet. Instantly, in the same minutes as everything else, and then it stays. Which means the flood maps are wrong the moment it happens. Not the tsunami maps, the ordinary flood maps. The ones for regular winter storms and high tides and river mouths doing what river mouths do. Every one of those has to be redrawn, because the land they describe is now lower than it was. Their modelling has the floodplain expanding enough to more than double the number of people, buildings and roads exposed. And because sea levels are rising anyway, if you run the same event later this century instead of tomorrow, that exposure roughly triples. So the tsunami is the thing that happens to you, and the subsidence is the thing that keeps happening to you forever, and the second one has no cleanup phase. There's nothing to clear away. The ground is just lower now. Some places would flood on ordinary tides that never flooded before, every month, indefinitely. That's the ghost forest, running forwards. Same mechanism, 3 centuries later, except this time there are towns in the marsh. The Oregon Resilience Plan, which is the state's own assessment, is refreshingly blunt about the recovery side. Their timelines have full service restoration in the western valleys taking 3 months to a year, over a year in the hardest hit coastal areas, and many years in the coastal communities that the wave actually goes through. Their point, and it's a fair one, is that businesses don't wait a year. If services are out for a month, businesses relocate or fail. So the long tail of this isn't rubble, it's people quietly leaving and not coming back. I'm not going to end this section on a death toll because that's not really what any of this is about, and I'd be doing the thing I've spent all night trying not to do. So let me end it on some ordinary stuff instead. There's an earthquake early warning system running across the whole region now. It can't predict anything. What it does is notice the rupture has started and get a message out ahead of the shaking, because radio is faster than rock. Which buys seconds, sometimes tens of seconds. That's enough to stop a train, open a fire station door, get a surgeon's hands clear. The physics of that is worth 30 seconds because it's genuinely elegant. The shaking travels through rock at a few kilometers a second, which we established. A radio signal travels at the speed of light, so if a sensor near the rupture notices it starting and shouts, the shout overtakes the shaking, and the further away you are, the bigger your head start. It's not prediction, it's just a race, and one runner is enormously faster. The other thing that exists is preparedness guidance that has quietly given up on the usual advice. The standard line for most disasters is have 3 days of supplies. On that coast, the official suggestion is 2 weeks, because the roads and the bridges and the water mains are not going to be back in 3 days, and everybody involved knows it. 2 weeks of being on your own, that's the actual ask. And the emergency managers who say it are at pains to point out that it's achievable, that you probably have more of it in the house than you think, and that you can get there gradually rather than in one grim shopping trip, which is a much better piece of communication than a death toll, and gets about 1% of the attention. Tsunami evacuation signs are just part of the scenery on that coast. Blue signs, a wave, an arrow pointing uphill, they're completely unremarkable there. Nobody looks at them. That's what success looks like, honestly. Information that's become furniture. And people get on with it, obviously. They buy houses, they open cafes, they have strong opinions about parking. The fault is a fact about the place the way the rain is a fact about the place, and you cannot run a life on a 50-year probability, so mostly nobody tries. I don't think that's denial. I think that's just what living somewhere is. There's more in the subsidence work than I've had room for tonight, and the segmentation research is still coming in, and by the time anyone watches this, some of these numbers will have shifted a bit. They do that. I said at the start that the thing I liked about this was that we know the evening. I like it more now than I did when I started reading, and I'll tell you why. Because look at what that knowledge is actually made of. A merchant's notebook in a coastal town in Japan, kept by somebody balancing his accounts. A village headman's report about water he couldn't explain. A stand of dead cedars still standing in a marsh 3 centuries later because cedar won't rot. Some grass under some sand. Layers of mud on the seafloor sorted by weight. And a story about a bird and a whale, built with hooks on it, so it could survive 12 generations of people telling it to each other in the dark. None of those things were made to be evidence, not one. The headman wasn't leaving a note for seismologists. The trees weren't recording anything, they were just growing. The people telling the Thunderbird story weren't filing a report, they were doing what people do after something terrible, which is put it into a shape you can carry. And 3 cultures who never met, on 2 sides of an ocean, across 300 years, accidentally co-authored a document none of them knew they were writing. Then somebody finally sat down and read all of it at once, and out fell a date. That's a nice thing to have happened, I think. Out of a fairly grim night. The fault's still there, it's still stuck. The plate is still going under at about the speed your fingernails grow, and it'll be doing that tonight while everyone above it sleeps, and it'll do it tomorrow, and the strain will keep going in the way it's been going in since the year we've been talking about. That's not a threat, it's just the arrangement. It was the arrangement long before anyone was there to have an opinion about it. I've got at least 2 more of these in me from the reading I did for this one. There's the slow slip, the earthquakes nobody can feel, which I still don't think I properly understand. And there's the whole scrap about the mud, which is nerdier than tonight, and I mean that as a recommendation. Anyway, that's the 26th of January, 1700. 9 in the evening, more or less, a Tuesday. Sleep well.